This is an attempt to lecture as I would if I had a whiteboard with me and you had a periodic table next to you. I would probably, while watching this, open up a periodic table, and you can pause this for a moment to do that if you're able. Hopefully you see right now my full screen. I have a periodic table, my upper left. The bottom portion, bottom right, is completely blocked, and that's fine because we're interested in the first 25, and if you notice, the first 25 are there, starting up at the top left corner, the blue hydrogen, jumping over to helium, and so forth, all the way up through manganese, number 25. Can you locate number 25? Yep, right there. That's manganese. So what I want to do is draw atoms. We're going to do that Bohr model. If you don't know what Bohr model is, you might have to refer back to the previous lecture, but it's not a big deal. It's simply a way we represent atoms, okay? And everything we need to draw a Bohr model comes right from the periodic table. There are some gaps in the knowledge, though, and that's what's kind of hard, is to find videos that give you absolutely everything. You get bits and pieces here, and your brain is left trying to fill in the gaps. Well, that's what I'm going to aim to do here. And there might be something we haven't seen yet called the octet rule. So before we get to drawing anything, I'm going to share with you what the octet rule is. So it's spelled octet, like 8, rule, the octet rule. And so there's many ways to say this. You can look up this definition and get your own definition if you'd like on the internet. Just type in octet rule in chemistry. But I'm going to put it in my own words. You can put it in your own words. But basically, what it's referring to is the energy levels around atoms. Okay? So every energy level, and when we say energy level, we're talking about shell. You might have seen it referred to as a shell. Every energy level wants to be full. And to be full, that is happy, okay? Or another way of saying it is stable, okay? They want to hold as many electrons as possible. And that's just the best way to say it, okay? The octet rule. So every atom on the periodic table, every element on the periodic table wants to be stable. That is, it wants to be happy. It wants to be full of electrons. Now, to be honest, it doesn't care what it has to do to get them. So that means some atoms will have to give, and some will have to take more. Now, I haven't identified yet what we're talking about, have I? The octet rule, every energy level wants to be full, happy, or stable. When I say energy level, what is inside the energy level? What are in those shells? Electrons, correct. So that means every atom wants to have all of its energy levels filled with electrons. And when they're filled, the atom is, as we say it, happy or stable. If it's not filled, it's unhappy, not stable, and therefore it's going to be very reactive, very interactive. It's going to be sad. It's going to interact or react in order to become stable or happy. So what we're talking about here are electrons. That means some atoms will have to give and others will have to take more electrons in order to fill all levels. Now, I'll tell you what, the only ones we're interested in, or what you might have heard in the previous lessons, is the valence electrons. So electrons fill the inner levels first. And as the levels, whoops, inner is 2 ends. As the inner levels fill up, all of a sudden, you can't fit any more electrons into it. The next electrons that come in will have to go to the next energy level, okay? So electrons fill the energy levels first. and then additional electrons must go to the next level, and so on, until it has all the electrons it can hold, right? Okay, so the octet rule here states that every energy level wants to be filled. That includes the innermost ones and the outermost ones. Now the innermost, and just think about this logically, if we have 3 energy levels, the only reason we're in the 3rd energy level is because the first 2 have been filled. So it fills the first one, there's still more electrons, it fills the next one, oh, there's still more electrons, and it begins to fill the 3rd energy level. Okay, so what we're always primarily interested in is that outermost energy level, okay? And that is the valence. All right, the outer valence shell. Valence shell is the outermost energy level for a given element. So let me make sure this is all correct here. Additional electrons must go to the next level, ... until they fill the valence shell. That is the outer, until we'll say outermost, that is valence shell. I'm gonna do it like that. Valence shell is filled. All right, so the outermost valence shell level is filled. So the next question is, how many electrons, right, can fit in these shells? Well, each shell holds a similar amount. What number do you think it is that they hold? Correct. Octet means 8, but there's an exception. So let me just tell you, the first energy level holds only 2. But the second, third, and fourth, if it matters to us, fourth, all hold up to 8 electrons. Okay? And so because 8 seems to be the magic number, 2 in that first energy level really only applies to helium and hydrogen and lithium and a little bit beryllium. And we'll see here in just a few moments. So let's just remember that rule, the octet rule. Every energy level wants to be filled. Every atom wants to hold as many electrons as it possibly can. And what would you suppose limits the ability to take on more electrons? Think for a moment. Electrons, let's recall, are negatively charged. All right. What is positively charged? Protons. And if we remember from past lectures, protons tends to equal electrons. So if we want to know how many electrons need to fit around an atom, all you got to do is look at the atomic number. That tells you the number of protons. So hydrogen, if there's 1 atomic number, that means 1 proton. It means only 1 electron. We're only going to have 1 energy level. Okay, so I'm going to go ahead and begin to draw here. That doesn't look like I'm drawing. Let me try this again. Here we go. So I'm just going to do hydrogen because it's simple. Well, you know what? Let's do lithium. So lithium is number 3. Line number 3. Okay. So the first thing I do in doing a Bohr model is I write the atomic symbol, the elemental symbol, lithium. I'm going to look up. I see that its atomic number is 3. That tells me it has 3. All right, P plus. That reminds me that it's protons that are positively charged. So I just got that right from the periodic table. Lithium is Li and 3. So this represents my nucleus. Now I know other things, there'll be balls. That's a proton. That's a neutron. That's a proton. That's a neutron. That's a proton. That's a neutron. I don't want to draw a bunch of balls. It's going to get pretty confusing. I don't want to sit here counting 1, 2, 3, 4. Forget it. Okay. So let me undo those. And what we're going to do instead is here we go. just write lithium 3p plus, okay? And that's my nucleus instead of a bunch of balls. Now, what group and period are lithium in? I see that the period is the second. So hydrogen to helium, this is the first period, and lithium is in the second. You can number them on yours if you want to. Oh no. Ooh, that was close. So that tells me I'm going to draw two. Now, you may or may not have heard this yet in the lessons, so I'm telling you now, listen carefully. The period tells us how many energy levels it has. So 1 ring, 2 ring. I don't want, I guess you could, if you want to draw the whole thing, you can, just gets kind of sloppy. So there's the 2 rings surrounding lithium. And then it's in the first group. Okay, so we had 1, 2, skip a few, 3, 4, 5, you get the point. This is sloppy. So if it's in the first group, that tells us something else very special about all those atoms in that group. It has 1 valence electron. Think about that. All right. So if we're talking about the valence shell, and I'm telling you that the groups, the up and down, tells us the number. So if we're in group 1, we have 2 valence electrons. If we're row 2 or group 2, it has 2 valence electrons. These have 3 valence electrons. These have 4 valence electrons. So lithium is in group 1. So let's put our 1 electron right there. And now, as I just mentioned, the electrons fill the inner levels first. Additional electrons then go to the next. So if I have 3 protons, I need 3 electrons. The first level only holds 2. So I'm going to put my 2 here. And then I'm on my third, and hey, look at that. We're done. How many negative charges do I have? 3. How many positive charges do I have? 3. So that's neutral. And that's how this lithium atom exists. Okay. I'm going to go ahead and pause here so I can erase all this. Okay. So got clear of that. Hopefully you wrote that down. You can always rewind and go right back to it. So I want to summarize the octet rule right here. Energy level. So how many electrons does the first energy level hold? Anyone? Anyone? 2. How many electrons does the second energy level hold? I'm here to tell you it holds up to 8. And the next energy level? 8. And the next energy level? 8. And this is why it's called the octet rule. And this might help. What's really cool then is now you can really begin to appreciate the organization of the periodic table. I'm going to put a line right through here. Okay, so there's our so these are the various energy levels or orbitals around, and there we go. I'm just going to doctor that up a little bit. Okay, sorry. Wasting time here. Okay, so let's do a few more examples. Okay, since we've done hydrogen, we've done lithium. Did we do hydrogen? Let's do hydrogen. There's my nucleus. Remember, I want to let the atomic symbol represent my nucleus. So this is a nucleus. And I look, and again, the atomic number is 1. So I have 1 proton with a positive charge. What period is it in? Well, it's in the first period. It's in the first period. That tells me it has 1 shell or 1 group going around it. What period is it in? 1. What group is it in? 1. So that tells me there's 1 electron, 1 valence electron in that group. Okay, and we're done. Now again, I know some of us we would like to see 1 proton that's positively charged surrounded by 1 electron that's negatively charged. That's another way of representing it. That's not wrong. Some might just do a proton electron. We have a negatively charged electron and a positively charged proton. Hydrogen is the simplest and smallest element on the periodic table. This is really all there is to it. One electron right there and one proton. Whether you want to draw a solid line or a dotted line or a half line, that's up to you, so long as you understand that there's orbitals that surround the nucleus. Okay, this is one way to do it. And it's fine, but honestly, again, once we get to the higher and the bigger numbers, that's going to be a lot of circles and a lot of, I guess it's going to get sloppy. So again, what do I like to do? Let me get my eraser. I like to just draw half the atom, okay, and this is my Bohr model, and I use numbers and symbols such as 1p plus and 1 negative, and that means there is an electron right out there. Okay, let's do lithium again, because I want you to see this. Lithium, what's the atomic number? Look up. I got a block kind of, but lithium is number 3. Tells me it has 3 protons. And what period is it in? 2. That means it has 2 rings, 2 shells that go all the way around. And what group is it in? The first. That tells me it has only 1 electron. You could have put it up here if you wanted, or down here. 1 electron in the valence shell. Which means if there was 1 out here, that this had to be filled first. And it holds up to 2. All you gotta do is look back on your notes. And there we go. Lithium is holding all that it can hold. But is it happy? Is it stable? No. It's neutral because 2 plus 1 is 3. We have 3 negative charges and 3 positive charges. It's neutral, but it's not stable. It's not happy, right? So as I mentioned in the notes, lithium will do whatever it needs to do, or it might gain some. It would have to gain how many? Well, with the second energy level, it would have to gain 7 more electrons to become stable. Much easier for lithium to just give. Remember, it can give or take. And in this case, much easier to just give it away. And now all energy levels are filled, aren't they? But you notice something different. Now we only have 2 negative charges because we gave away an electron to someone. And we still have 3 positive charges. So now lithium becomes what is called lithium ion. And the way we represent that is we draw, say, lithium. And what's the difference here? It looks like a positive 1. Positive. Okay, so that's a lithium ion. We just say Li+. Now we're going to get more into that next week, but this is a good introduction to it. Okay, so let's look at hydrogen here real quick. And hydrogen, how many shells does hydrogen have around it? 1. And how many electrons does that first shell hold? 2. But how many does hydrogen have? 1. So what does it need to do? Give or take? Well, it can do either, but it wants to take on 1. I'll tell you this, 1 proton in the universe, though, is not going to pull much, even though you would tend, and remember, just like in the lectures before, hydrogen's a little different. It's weird. It's not a metal, but it's over here with the metals. The reason why it's where it is, even though it's light blue, it's in the first column, is because it behaves very similar to lithium. It's actually going to release this electron. It releases it because it's just really too small. It doesn't have enough positive power to pull in another electron. So what ends up happening with hydrogen, and this is a special case again, is that it will lose that electron. And now hydrogen has what charge? That's right, positive charge. Oh, where's my annotation? So we'd represent that by just writing H+. If I saw that H+, just like I do with the lithium, I see an H+. What I know is because the atomic number never changes, it still has 3 protons for lithium. And I know hydrogen still has 1 proton. But because there's a positive charge on it, I know it must have lost 1 negative charge, that is, an electron. Same thing with hydrogen. If I see H+, I know that's a hydrogen ion. It lost an electron. All right. So I want to draw a third one more for you. You can pause and digest that if you like and get me to repeat something. Of course, if you're keeping your notes, I'm going to draw sodium. Try to find sodium. Get it? It's number 11. All right. So sodium, let me get my eraser here and clear some. All right. So sodium, nucleus, Na. There's my sodium nucleus. Again, I don't draw a bunch of balls and circles, but I do need to represent the protons and neutrons. So I look at sodium, number 11. It's right over here, also in the first group. So I'm going to write 11p plus. So I know it has 11 positive charges in the nucleus. Why am I not messing around with the mass? Why am I not mentioning the neutrons, you might ask? Frankly, they don't matter. They don't matter to chemical bonding and chemical reactivity. They're not charged. They're neutral, so they don't influence reactivity. There is something to be said for isotopes, and we'll talk about that later. But in chemical reactivity or even in biology, neutrons don't matter. So I'm leaving them out for now. Although we're not far from figuring them out, and we'll talk about it. Maybe I'll mention it here in a little bit. So 11 protons. What period is it in? Let's count. 1, 2, 3. Okay, it's in the third group. So I'm going to have, this gets kind of big here. 1, 2, and you can 3. So I have 3 rings. If you would like, you may complete those circles. And that's it. So 3 shells, I know that because it's been organized according to the periodic table to have 3. Now, what group is it in? 1. What does that tell me? Number of valence electrons. So I know it's only going to have 1 electron out here. I also know that the electrons are fill the innermost shells before they get to the outermost. If that's so, then this one, the middle one, must be filled. And how many does it hold? Well, the second one holds 8. So there's 8 electrons here. And the first one holds how many? 2. So there's 2 electrons here. 8, 9, 10, 11. Hey, look at that. 11 negative charges, 11 positive charges. We are neutral. And that's the way the sodium exists in nature. Now, it will not exist long like this. Why? Because it's not happy. It's not stable. It is very unstable. Why is it unstable? Because it doesn't hold all the electrons it can in its outermost energy level. Do you think sodium's going to give or take electrons away? Correct. It's going to get rid of it. It's much easier to get rid of this one. Oh no, I didn't want to erase that. It's much easier to get rid of this 1 than it is to pull in 7. So as we look at that now, we have our 11 positive charge. What am I doing? We have our 11 positive charges, but only 10 negative charges. That leaves us with the difference of positive 1. So that means sodium is going to be an ion that is positively charged, a sodium ion. How do we write that? Na, the little positive up here. And that's your sodium ion. Notice, do you remember what hydrogen looked like once it became stable and happy? Do you remember what lithium looked like once it became stable and happy? Yeah, that's right. That's why all these are in the same group on the periodic table over here. Okay? Because potassium, rubidium, all of these have just 1 valence electron. And that determines much more about their reactivity. than anything else. Valence electrons are what you want to know about when it comes to bonding. I want you to draw now beryllium. Okay, draw beryllium. Pause it and try that using this Bohr model. Okay, I've cleared my board. Hopefully you gave yourself an opportunity to try that. So beryllium, Be is my atomic symbol, and I allow that to represent my nucleus. Beryllium has an atomic number of 4, so I'm going to put a little 4 P plus. That reminds me I have 4 positive charges in that nucleus. What period is it in? As I count down, I have 1, 2. I'm in the second period, so it tells me when I have 1, 2 shells that go all the way around it. Another good reason I don't fill in half of this is so I can write out here in the edges, as I'm about to with the electrons. Now, I'm going to do mine a little differently. Let's just say I know now, because of its position, that there's only 2 shells. Well, I know the first one has to be full, and the first one only holds 2 electrons, so there you go. Now, how many go out here? How can I find that out? Correct. I just look at my proton number. My proton number tells me my electron number. So if I have 4 protons, how many electrons do I need? 4. And I already have 2 because the first shell only holds 2. So how many electrons go out here in the valence? Correct. So that's another way you can do the Bohr model, just by nature of knowing the octet rule. And you have 4 protons, then you know it's going to be 2 and 2. Okay, well, there you are. That's what beryllium looks like. If you want to complete those circles, you are welcome to. Okay. Now, I'll go ahead and ask the question, is beryllium stable? Is it happy? Does it have all the electrons it can hold? Well, in this second energy level, we know it holds up to 8, and we only have 2. Is it easier to take on 6 or to release 2? Well, hopefully you're getting the hang of this, and yes, it's going to be easier to release 2. Therefore, what happens to beryllium? It's going to inherit, once it releases those 2 electrons, it's going to have a positive 2 charge. Okay, you can write that better, but it should be a positive 2. And that's a beryllium ion. Okay, why does it have positive 2? Well, it still has 4 positive protons, but having lost 2 negatively charged electrons, the charge overall is going to be a difference of positive 2. Okay, so let's do one last one. And again, we'll do one from the other side. So if you do magnesium, you'll find the same thing. Beryllium, magnesium, calcium, the orange, the alkaline earth metals, those 3 all have 2 valence electrons. So you don't even have to draw anymore necessarily. You know just from looking at where it's at in the periodic table that it's going to be a positive 2. Magnesium will be a positive 2. Calcium, guess what the charge is? That's right, positive. That's a positive sign, positive 2. Isn't that cool? Just like hydrogen, lithium, and sodium and potassium all have a positive 1. Something special happens here when you get across. Look at full carbon. Carbon is in group 1, 2, whoops, you can count them with me, 3, and 4. Wow. What do we do with that? Does it want to give or take? Neither. It shares, actually, but we'll get to that next week too. So let's go ahead and come over here. Now we're on, what should we do? Let's do fluorine. Okay, I'm going to do fluorine, and then I'm going to wrap this up and let's be done. F, that's my atomic symbol for the nucleus. I see the atomic number for fluorine is 9, so 9 protons. And let's just fill in the shells because we know there's 9 protons. I need 9 electrons. So let's draw one ring. It's just a little different way of doing it, but you'll see it's the same thing. How many electrons does the first energy level hold? Yep, 2. But we had 9 to place. We've only got rid of 2. That means we need to put 7 more. So let's go ahead and put another ring out here. And, oh, well, you know what? The second ring holds up to how many? 8 for the octet rule, but we only have 7. So there we go. And we're done. We have accounted for all the electrons. 9 protons, 9 electrons. It is neutral. But is it happy? Is it stable? No, it's not. And so fluorine will react and interact in such a way as to gain all the electrons it can in that outermost shell. Now, in this case, we have 7. We're 1 electron shy. So it will interact clearly. You know who would be a good partner for fluorine? Sodium. Why? Well, look where it is, number 11. It had 2, right? And then it had 8, and then it had 1 electron in its 3 shells. So sodium really quickly will get rid of that 1, and where might it go? You can see that happening, right? We're getting a little bit ahead of ourselves here, so this is bonus information, but you can see how that electron might come over here to satisfy this one. And now fluorine, even though now sodium has 10 negatives and 11 positives, so we have a positive sodium. We already covered that one. But now look at fluorine. With an extra negative charge attached in order to satisfy the octet rule, we have 8, 9, 10 negative charges, and we have 9 positive charges. What's the difference? Well, we have 1 extra negative charge. So fluorine becomes fluoride ion. And you can see where the chemistry is going to begin. This is a match made in heaven. When you have a positive one and a negative one in the same room together, you're going to form what is called sodium fluoride. And that, my friends, is what's working on your teeth right now had you brushed them today. Sodium fluoride is the active ingredient in toothpaste. And this is the form that it takes. This is sodium fluoride. And that's how they make it, because it's beautiful. For every 1 fluorine atom, you have 1 sodium atom. Hey, I got an extra electron here. I could use 1. Well, let's get together. And they do. The electron shares, the ions form, the ions of opposite ions attract, and they form a bond. Again, we'll talk about that next week as well. Okay, folks, that concludes this recording.